compare them to modern models. They didn't have a lot of detail, but everything they said was basically accurate. With the one exception, by the way, I think I mentioned this yesterday, but just in case, the rate of sea level rise has been slower than predicted.
Oh, because of the little particles, right?
Well, there's a number of reasons why it's slower than predicted. A lot of our extra water, so to speak, we thought that there would be extra water in the ocean from melting snow. A lot of that's being captured by dams. More and more water lives on land. And so a lot of the extra water volume of the ocean is now on top of the land masses. Separately, the ocean didn't heat up quite as quickly as possible because of the rates of heat transfer in deeper water. I want to remind everybody that the ocean is rising not because of extra water. That's only 10% of sea level rise. The ocean is mostly rising because of hotter water occupies more space. Ocean expansion is about 90% of sea level rise. Interesting fact, right?
So, now there's more fresh water on Earth than there was?
Now there is marginally more fresh water. There's way less frozen water. There's slightly more salt water, but the salt water is getting bigger. It's not as fast as we thought it would in the 80s.
And they were right on target.
The simulation shows that there was a significant increase in rainfall in this entire region of Africa, circled in red here. This was associated with stronger monsoon winds. When we finished this experiment, we were excited to notice that this area corresponds closely with regions that now have small lakes and then had large lakes, and with regions with no lakes today that had very big lakes at that time.
Kutzbach's success and many others like it make climatologists feel their computer models should be taken seriously. While these models may not be perfect, they're our best hope for understanding the future. And as we'll see in our next section, if we let the predictions come true, the cost to people and nature could be horrendous. For the world is a lot more dependent on today's climate, as we'll see next. By the year 2050, computer climate models say the sea level will rise significantly. The basic reason is simple. Steve Schneider.
If you increase the temperature of the planet by, let's say, 4 or 5 degrees, that's going to do the same thing to the oceans that heating a fluid in the thermometer does. If you heat a fluid, it rises, it expands and rises up and is constrained by the thermometer. Well, if you heat the oceans, it's going to expand and it's constrained by the walls of the continent. So we're going to get sea level rise.
What's more, melting water from the polar ice caps could push the level up even further. Almost every country in the world could lose valuable coastal land. In the United States, that includes Cape Cod, Long Island, Florida, and Louisiana. An entire island nation, the Maldives, could be flooded off the map, creating the world's first greenhouse refugees. The Indonesian islands, with 230 million people and 40% of the world's coastline, could become a nightmare, as would low-lying deltas throughout southern Asia. By the year 2050, most of these areas would still be a couple of feet above sea level, so they wouldn't be permanently flooded. But being just a little higher than the water doesn't count for much. More than anybody else in the world, the people of Holland know what it's like to fight the sea. 2/3 of their country is right around sea level, and the land here stays dry only because of an elaborate system of dikes, which stand guard along the entire 1,000-mile coastline. Towering 30 feet above the high tide mark, these earth and stone dikes seem like overkill, especially when the sea is so calm below. But in 500 years of trying to conquer the sea, the Dutch have learned a hard lesson. Overkill is necessary for one reason only: severe storms. 1953, the coast of Holland. High winds pushed the tide 16 feet above normal. enough to overwhelm the dikes that existed at that time. Frantic efforts were made to stop the sea from surging inland, but its force was too powerful, and the country suffered terribly. Nearly 2,000 people died in this tragedy, and the survivors vowed never to let it happen again. The cost of fulfilling that pledge was staggering. According to Pier Valinga, Holland's leading authority on dikes and sea level rise.
After the 1953 storm, we had to heighten the dikes by about 2 to 3 meters, and that cost over $10 billion. And that's, well, in the order of 0.5 to 1% of GNP on an annual basis. And, well, that is a continuous amount. It's not just construction, but it's also maintenance, the dunes and the dikes, and it comes back every year.
Constructing dikes is serious business on the scale of building a first-rate national highway system. Wealthy, developed countries could perhaps afford to follow in Holland's footsteps. But in developing countries like Bangladesh and Indonesia, the expense would be out of reach. Money isn't the only issue either. As well as laborers, thousands of skilled designers and engineers are required to do the job. In countries that don't have these resources, vulnerable coastal towns and cities might have to be abandoned. Either way, building dikes or abandoning valuable land, allowing the sea to rise will mean a tremendous waste.
When the sea level will rise, as we expect now, we must do the same thing again, and it will cost another 10 billion or even more. And, well, technically it's possible, but it's such a wrong way of spending money, I would say. We could better invest that in keeping down the rate of climate change.
If we don't keep down the rate of change, humans won't be the only ones to suffer. Take the famous Florida Everglades National Park. Much of this ecosystem depends on its connection to salt water, so walling off the sea makes no sense. But to biologist Larry Harris, the alternative also spells disaster.
If the projections are correct, the sea will come up about 1 foot within the next 25 to 40 years. That means that the edge of the sea that we're standing on today will occur 10 miles north of here by about the year 2010. And if the sea level comes up 2 or 3 feet, then the entire park will be lost. And we fear that Everglades National Park may be one of the first national parks lost from the face of the earth.
At stake here is a treasure chest of unique and endangered wildlife, including countless species of rare wading birds. The American alligator, the manatee, an ancient aquatic cousin of the elephant, and the Florida panther. They live in a closed-in world, quite unlike the time when the Saharan monsoons disappeared, when people and animals had plenty of room to move. If the park is squeezed smaller by rising water, these animals will be forced up against an insurmountable barrier, which stands between the Everglades and other wetlands lying to the north.
The animal species, of course, would normally be able to move up the peninsula if there weren't human habitation and human blockage. But with all of the interstate highways and the chain link fences and barking dogs and golf courses, the wildlife will be caught between the devil and the deep blue sea.
A completely different problem will plague animals in wild areas away from the coast. In many cases, the plants and trees they depend on for survival only grow under specific regional climate conditions that have been stable for thousands of years. But computer climate predictions show entire temperature and rainfall belts shifting several hundred miles by the middle of the next century. The only way for vegetation to survive is to follow. Plant species can move up to 1/2 mile a year, as their seeds are blown by the wind or carried by animals. But just as in the Everglades, most wild places are hemmed in by towns, cities, and farms. so there won't be any escape route. Unless we actually pay for massive relocation, forests could end up looking like this as they get marooned in the wrong climate. And of course, the animals depending on these forests would be trapped at the same time. And then there's the entire world's food supply. It's also threatened by rapidly shifting climate patterns. A disturbing example of what high temperature and reduced rainfall can do to food crops was the American drought of 1988. That summer, the grain harvest was devastated by the unusual weather. Because grain dealers still had stockpiles from previous years, which they nearly emptied, consumers hardly suffered at all. But what if there had been another bad harvest the next year, and then the year after that? To Lester Brown, president of the World Watch Institute in Washington, this is a scenario we're likely to face if we let global warming continue.
When stocks are so low, the world becomes very vulnerable to another short harvest. And as we look ahead at the prospect of more and more hot summers, like the summer of '88, the future food security of the world is becoming more and more questionable. We could see food security replace military security as the principal preoccupation of many governments in the world during the 1990s.
Food crops are extremely sensitive to weather. It doesn't take a whole summer of heat or drought to reduce yields severely. In the case of corn, for instance, just a few 95-degree days in the middle of the growing season can ruin the harvest. For corn to develop, pollen must fall from the top of the plant onto the silks below. Each silk corresponds to one potential kernel on the ear of corn. Silks that fail to catch pollen usually result in missing kernels. Here's the problem. If the temperature hits 95 degrees, the leaves of the corn plant curl up to conserve water, covering the silks. Now, when the pollen drops, many silks won't get any. Worse yet, if there's a hot spell a little earlier, the silks won't grow, but the pollen will. So they can end up missing each other altogether.
When that happens, you can get a severely reduced corn harvest. Corn is important because it accounts for 2/3 of the U.S. grain harvest and 1/8 of the world grain harvest. When the U.S. corn crop is sharply reduced as it was in the summer of 1988, the entire world feels it.
If climate gets consistently warmer, corn production might have to shift to Canada, without American farmers, of course. But that's easier said than done. One of the factors making America's corn belt so productive is deep, rich soils, and the thin soils of Canada aren't nearly as good. Growing the same amount of corn there would cost much more, if it were possible at all. It's true, some agricultural zones might benefit from global warming. For instance, much of the best land in the Soviet Union is underused today because the weather's too cold. But there are many more regions where agriculture would probably suffer, like Southern Asia, where coastal rice production could be ruined by salt water flooding from the sea. In effect, we'll be playing roulette with our food supply if we allow the climate to change.
The evolution of agriculture, reaching its current level of productivity to the point where it will support 5.2 billion people, is closely key to the existing climate system. We have no guarantee that if that climate system changes, we'll be able to feed 5.2 billion people as we do today.
To make matters worse, there will be around 10 billion people to feed by the year 2050, if the world's population continues to grow at its present rate. This would create twice the demand for food at the same time supplies are threatened. In a greenhouse future, other vital resources we depend on, like water, may no longer be available where we're accustomed to having them. We'll be prepared to deal with the consequences. What, for instance, would we do if the water coming down this river suddenly slowed to a trickle? This is the mighty Colorado, a legendary blue streak running through one of nature's wonders of the world, the Grand Canyon. And this is a man-made canal carrying some of the Colorado's water through the desert of Arizona. It's part of the Central Arizona Project, built at a cost of $4 billion to supply the growing water needs of the state's largest cities, including Phoenix. Like most users of the Colorado, the residents of Phoenix regard their water as something that will always be there. It's almost beyond imagination to think that global warming could take a lot of that water away by the middle of the next century. Just on the outskirts of the city, there's a grim reminder of what much of Phoenix and the entire Southwest would look like if it weren't for the water from the Colorado. Peter Glick.
The Colorado River is the lifeblood of the Southwest. By most standards, it's not a very big river, but it's just about the only water in the southwestern part of the U.S. The Colorado River is used for power. It's used for irrigation water in the United States and Mexico. It's used for drinking water in Phoenix and Los Angeles and San Diego.
Peter Glick is a leading authority on the world's water resources and on the threat to those resources posed by global warming. Today, he's at Lee's Ferry, Arizona, working with the federal agency that keeps track of how much water is flowing down the Colorado. Official measurements have been taken here ever since 1922, when the river's water was allocated among the various users. Today, every last drop is spoken for, so precise readings are crucial. The amount of water passing by is calculated from the rate at which the propeller blade spins. If this propeller ever slows down, the users of the Colorado will be in trouble.
0.2, 30 and 46 seconds. 30 revolutions, 46 seconds. Right.
Global warming could permanently slow down that propeller blade. And that's because the small streams which feed the Colorado come mainly from the Rocky Mountains, where some climate models predict a decrease in snowfall. On top of that, even if the temperature rises only a couple of degrees, the many reservoirs along the river would lose huge amounts of water from additional evaporation. To make matters worse, higher temperatures would also increase demand. All this would mean some hard choices.
If there are decreases in flow in the Colorado, we have to decide who's going to get cut off. Arizona in particular is fairly low in the pecking order, and California is fairly high. We've also promised water to Mexico as part of their allocation of the Colorado. They are at the very end of the river. Do we short Mexico? Do we give Mexico a little bit less water so that we can continue giving U.S. users their share? Do we short U.S. users and give Mexico their full share?
The same hard choices might have to be made for major rivers worldwide that are also being used to capacity. Many flow through several countries, and this could be a prescription for disaster. The Nile, for instance, crosses Ethiopia and Sudan, then flows to the sea through Egypt.
Egypt has already said that it's willing to go to war over the Nile River. Just like the Colorado is the lifeblood of the Southwest, the Nile is the lifeblood of Egypt. There is no other water there.
Rapid change to ecological systems we now depend on. That's the threat of global warming. Having to find new places to grow crops, or new crops to grow where old ones wounded. Having to protect thousands of miles of coastline, or relocate millions of people. Having to cope with a change of climate that's coming much faster than any other climate change before. Steve Schneider.
15,000 years ago, the Ice Age began to break up. There was ice sheets literally a mile high over New York City, across through the Great Lakes, over most of northeastern Canada and parts of Europe. And over the next 10,000 years, the ice disappeared. Sea levels rose 100 meters, 300 feet or so. Forests moved thousands of kilometers. Literally, the ecological face of the planet was revamped. It took 10,000 years to warm the planet up only 5 degrees Celsius, about 9 degrees Fahrenheit. We're talking now about change on that magnitude in a century. So we could be modifying the climate and the whole Earth's environmental system at a rate something between 10 and 100 times faster than nature. And that's guaranteed to have nasty ecological surprises.
The sense of urgency Schneider and other climatologists feel is largely based on their computer models. Yet it's possible these models are too pessimistic, because they can't handle some factors which could dramatically alter the pace of change. University of Chicago climatologist V.L. Ramanathan recently jumped into the middle of the controversy when he asked, what could happen as the oceans get warmer?
As the oceans warm with the rest of the planet, the moisture evaporated from the ocean will increase, just like you see the vapor coming out of this hot coffee cup. Now, what happens to this vapor as it rises into the atmosphere? It can form clouds, just like you see clouds forming on this cold glass.
Clouds influence the Earth's temperature in two opposing ways. On one hand, they reflect sunlight back into space, shading the Earth's surface and cooling the planet. The thicker a cloud is, the greater its cooling effect. On the other hand, clouds create their own version of a greenhouse effect. They form a blanket over the Earth which traps heat. The higher a cloud is, the more heat it traps.
There's a lot of clouds right over the Indonesian monsoon region, where we saw a lot of...
Using computers and satellite data, Ramanathan has determined that on average, clouds today cool the Earth more than they warm it. On this basis, many skeptics suggest extra clouds will stop the world's temperature from rising. But Ramanathan says it's more complicated than that.
If this increased cloudiness is going to be low, thick clouds, that can have a cooling effect and sort of counteract the greenhouse warming of these pollutants. If, on the other hand, this increased cloudiness is going to be upper level but thin clouds, they can trap enormously more heat radiation and sort of amplify the greenhouse warming, which I consider as a very disturbing but plausible scenario. The fundamental issue is any combination of the cloud systems can form, so in a sense the future of the planet relies on how the cloud distribution is going to adjust to the heating of the ocean.
So the impact of extra clouds could go either way. But now consider another complicating factor that can't do anything but make this.
So they could go both ways. Look up. Which is it? But here's the problem. The way they said is not right. I told you, this movie's old. It's shockingly accurate. There are two things in the movie which are probably, worth mentioning, not exactly accurate. One, as I said at the beginning of the period, the rate of sea level rise. But two, this is apparently a really sticky wicket in climate projections. All the models have been revised and re-revised as a variety of research pushes this one way or the other. We know that the planet gets hotter, so we know that makes more water vapor, so we know there will be more clouds, and what's that got to do with temperature? Today, the best consensus I have heard is that high clouds have more ice, thus reflect more light and cool the Earth, but low clouds are warmer, more water vapor, and water vapor causes heating. So contrary to what the movie just said, it appears that higher clouds would cause cooling by reflecting sunlight, because the ice is shiny. High clouds have more ice because it's colder up there. And that low clouds are like a blanket right on top of a warm body because of the water vapor. They trap and re-emit heat, which is not what the movie just said. It's the opposite of what the movie just said. If anybody here finds me good research that is compellingly decisive on this question, I'll be curious to consider it. I'm not talking like LA Times / Wikipedia. I mean, if there's like primary literature that settles this issue in the last few years, I would give you extra credit if it's compelling. Yeah.
So is there any way to determine if a cloud will form high up or low down? Or is it just random?
I guess, but not, I don't know. So, the altitude of clouds has a lot to do with whether on average air is rising or dropping there, and like how the winds combine. Basically, you're talking weather, not climate. You know what I mean? Weather's like moment by moment happenstance. And so, yeah, statistically it seems like high clouds are more likely or high clouds are less likely, but no, there's no certainty about that. Hey, James Bell, put your cell phone on top of one of those houses. Thanks. There's been a lot of debate about which clouds would be more likely. Like, seriously, this is one of those questions which the scientists, like, sort of like, who's the greatest basketball player of all time? Like, there's so many ways to talk about this, and everybody goes, but if you base it on this, it'll be more high clouds. And it's like, yes, that's clearly true, but if you base it on this, it'll be more low clouds. And, like, it's sort of a... By the way, that variability does not mean that there's doubt about global climate change. That variability is about just how much warming over how much seasonal variation, but it doesn't change the fundamentals of climate projections. Yeah?
Do you know the actual rate of sea level rise?
I don't. Current science has like measured a fairly clear, consistent rate.
But it's less than 1
the last few decades.
Less than 1 foot a year is what they said in the video.
I think that they were saying that by the year 2050 it could be as fast as, but I don't think that. That to me sounds high even by the year 2050.
3 millimeters a year.
Right now, 3 millimeters a year, that sounds a lot more credible. Yeah. Yeah, you're the best.
Wait, worse. Buried just beneath the floor of the Arctic Ocean, and also beneath the Arctic tundra, are vast quantities of a substance.
What substance?
Good kid. Cause the world's temperature to rise much faster than the models are projecting. The substance? Methane hydrate. A combination of methane gas and frozen water. It may look like a snowball, but this is 90% methane, a potent greenhouse gas. If global warming thaws the tundra and warms the oceans sufficiently, huge amounts of this gas could be released. There are many other complicating factors like these. They could make things better or worse. Climatologist Steve Schneider.
It might not be 3 degrees warming that we're looking at. It might be only 1 or 2. But if there's a 50% chance that we're going to be less than we think, there's also a 50% chance it's more. Maybe it's going to be 3 to 6. So what we're really doing is we're taking a coin and flipping it. And on one face it says moderate climate change. The other face it says unprecedentedly large climate change. And in my value system, that's not the kind of gamble I like for the planet.
Over 20 billion tons of carbon dioxide and other greenhouse gases now go into the atmosphere every year, a rate which has been growing steadily for the past 2 centuries. Eliminating these emissions fast enough to avoid climate change may be impossible, but that's no reason for inaction. The more we can cut, the less warming there'll be.
2 degrees warming is not nearly as bad as 5 degrees. And if it happens in 50 years, that's much worse than if it happens in 150 years. We can make a substantial difference in the rate of change. And it's the rate of change that is difficult for ecosystems to adapt to and for people to adapt to.
The biggest opportunity for cutting greenhouse gases lies with countries that emit the most. Together, North America and Western Europe, with about 10% of the world's population, produce about 40% of all greenhouse gases. Here, the choices of individual citizens can really make a difference. In the United States, for example, switching to cars that get 50 miles a gallon, double the current average, would cut U.S. greenhouse gases by 3%. Lester Brown.
The real question now is not how large a car that you and I can afford, but what the planet can afford. And the answer is the planet cannot afford very many gas-guzzling automobiles. Or if we're buying a house, how much insulation does it have? And if we were to insulate it better, not only how much would we save on the heating bill, but how much would we save on carbon dioxide emissions?
If all U.S. homes were well insulated, that's another 2% reduction in the nation's greenhouse emissions. Some solutions go beyond individuals. Today, the prices of coal, oil, and gas are misleadingly low because they don't include the potential cost of damage from global warming. But adding in this cost through a tax on fossil fuels would encourage conservation and also give an economic advantage to alternative fuels which don't harm the atmosphere. Generating a fifth of U.S. electricity with alternatives would reduce the nation's greenhouse gases by another 6%. Then there are CFCs. They cause a quarter of the world's greenhouse gas problem today. So until production stops, we should prevent them from escaping into the atmosphere. Venting CFCs, for instance, is still common practice in the servicing of auto air conditioners. But laws requiring recycling of CFCs could cut the country's greenhouse gases by another 2%. Planting forests could also help. New trees grow by taking carbon dioxide out of the atmosphere. So long as these forests are left alone, this carbon dioxide will never go back into the air. If the United States can plant an area about the size of Delaware, less than 1,000th of the country's land, that would soak up yet another 2% of the nation's carbon dioxide emissions. These 5 measures alone, 5 solutions among dozens possible, already add up to a 15% reduction for the nation.
There's no magic single thing to do. We need to reforest. We need to use energy more efficiently. We need to develop alternatives. We need to shape our lifestyle so we take one trip with multiple errands rather than multiple trips. Every one of these things are nickels and dimes, if you will. But if you nickel and dime long enough, pretty soon you get to half a dollar. You've got the problem half solved.
The world's developing nations also have an important role. So far, countries like China, Brazil, and India haven't caused much of the greenhouse problem. But as these huge nations strive to achieve modern standards of living, their energy use will skyrocket, and the increased greenhouse gas emissions could overwhelm reductions made elsewhere. The only way they can avoid this is by not adopting the same wasteful technologies which were used to build today's industrial countries, and that will require financial aid. As well, they'll need to control population growth. At current birth rates, the population of all developing countries combined will increase by nearly 4 billion over the next half-century. So many additional people will make the job of cutting the world's greenhouse gases even harder. Challenges like these will surely put world leaders in uncharted waters, creating the need for unprecedented levels of international cooperation. But the alternative to bold solutions will be a climate change that's catastrophic.
I'm very concerned because this is not a trivial change in the climate. This is going to cause, for me and my children and my grandchildren, enormous changes in their lifestyles. And I'll be gone, I won't be here, but they will have to deal with it.
What we now have to think about is how we can all become environmentally active, because we all have a stake in the future. We all have a stake in the future habitability of the planet.
If we're not willing to slow the rate of climate change or to stop climate change at all, we'd better be willing to deal with the impacts that climate change is going to bring. The changes in water resources, the changes in agricultural productivity, the changes in sea level. It's one or the other.
There's no doubt.
No. There you go. Don't even try it, Meryl. A little propaganda. All right. Are there questions that I could help you to understand the content here now?
Wait, so
yes.
How do clouds hold ice?
How do what?
Clouds hold ice.
Clouds are ice.
Okay.
You know. they're water, and if that water's hot, that's water vapor. If that water's cold, that water's ice. So different places that you see clouds, depending on the water temperature, they'll just be all fuzzy vapor, like these low ones that we get over here most of the time. Or when you see those high ones that look kind of like more wispy and linear, those tend to be like little ice crystals, very, very fine ice crystals. Yeah?
You see, like, the top of the atmosphere is like the higher you get, the colder it is?
Absolutely.
So, like, where...
There's actually a fancy temperature pattern, which is one of your first homework assignments.
Yeah, I mean, obviously heat rises too, so is there some, like...
As it rises, it dissipates, though. So, yes, heat rises, right? But when you put your hand over the stove, you're telling me it gets hotter when you go up further? Like, if you got fire on the grill in your kitchen, it's like hotter, 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 hotter. My hand's on fire. My God, the skin's coming off. Because even though the heat is rising, as it rises, it dissipates. Yeah?
How do greenhouse gases affect conditions on Mars?
Mars has no atmosphere. It has like 0.005% atmosphere compared to ours. No greenhouse activity. So Mars, at like noon, 3 p.m., I think the surface temperature is like 280 degrees, 320 degrees, whatever. It's like really freaking hot because there's no filter for sunlight. And then at like 4 in the morning, before the sun has risen, all that heat has dissipated, so it's like 180 negative or like 210 negative. It's like open space but cold.
How did we get our atmosphere?
We got the atmosphere from basically the baby Jesus.
Oh,
you know, like stardust and gravity and like fairies and leprechauns, and then like the stuff all clumps together. So our clump, you know, the planets are fundamentally different. So there's this like density dependency issue, like how far things expand from their initial like parent star, and then how much debris is captured at which times, and a lot of like probability and chance. And then each of the planets has a different elemental composition. So if you put percentages on each of those elements in the periodic table, right, each planet would have a different set of percentages. We have 98% this one, 70% that one, 30% that one, and different planets have a different blend. Then you give it a certain amount of energy given your distance to the star, and then you kind of add some probability about which collisions you get with which celestial bodies to have like secondary gravitational forces and other bits of energy or material. And then you get your planets. In other words, the baby Jesus. Yeah?
What does it mean by the axis like wobbling?
It does. Yes.
So it's the seasons are happening obviously from it spinning and hitting the sun differently, but what are the like little ice ages?
As it spins around.
The angle of an angle will always point at my map wall. See that?
But that thing changes too.
Except every 22,500 years, that angle actually has a full wobble. So it's pointing every year in the exact same direction minus a 122.5 thousandths of a circle. So anyway, that thing's like, basically every year it's making a little tiny incremental shift. So that in 22,000 years it'll have gone all the way around. Yeah?
Does that mean at some point there are no differences between like the north and like the south?
Yeah, those are the moderate seasons. And when we look at the fossil record, we have temperature records that are pretty good. So I can give you decadal averages back like 1.5 million years, I believe. And through those, you can see these records of history. I will show you on Friday the 6th that science. Yeah?
If that angle was pointing the complete opposite way, our season would be completely flipped, or would it have like a slightly less?
No, they would be... well, they would be completely flipped and then more severe.
Okay.
I think.
Yeah.
Kieran Tesser, so I think we're good.
If the North Pole would be pointed towards the sun, then all the ice caps would melt.
Not necessarily, because those shifts in temperature may not be necessarily to the point of melting the ice caps. Keep in mind that most natural variation in climate is within a range of a couple of degrees, going back like 300 million years. The full spectrum of all that up and down is like a couple degrees here, so top to bottom. So we're basically breaking out of the parameters of normalcy that we've had for hundreds of millions of years. Is that a hand?
Yeah.
Fine. Speak.
They talked about all these like super complicated, difficult ways to save 15% of our greenhouse emissions, but do you think that's a little bit like kind of a small difference, or do you think it would help?
Many ways to answer Kieran's question. For one thing, 15% of our greenhouse emissions in 1989 is chump change, pointless, irrelevant today, because we basically, I don't want to say doubled net greenhouse emissions, but we're way above what we were in 1989, and we may have significantly more than doubled some of the emissions. The point that we're making is the 15 wedges concept, how to lower a little bit at a time. And Stanford University wrote a fascinating paper that your reading packet alludes to. Yeah?
So the second part of that question, the role of developing nations, what is that?
That they have to think about not making the same mistakes that we developed nations have. Everybody's going India, India, China, China. Because if those countries get our kind of success, but we already sort of like set the framework so they learn how to do it better and faster and cheaper and out of control, then holy crap are we in trouble. And that's exactly what it seems like China and Japan are, China and India are doing right now. But I'm sorry, students, you all want to pack up, but I got a lot of stuff to talk to you about. We still have like 10 minutes in the period. I plan to use them.
Are they concerned? Like the Chinese government concerned?
I don't know. That's a lot of people we're talking about, and I don't talk to any of them.
You don't? Yeah. Oh.
First of all, Green Club event Saturday 9 to 12:30 at Royal Hondo. Check the book face. That's important because by April 30th, everybody who has 15 hours or more of environmental community service gets the Student Environmentalist Award, which is printed by this organization called Explore Ecology, which is the parent organization of Art from Scrap, which used to be a part of the Community Environmental Council. And you may not have heard any of these names, but it's kind of a big deal. And the paper you may not even get. One year they printed them, mailed them. The school didn't save them for me. When I showed up the next day, it was like, oh, whatever, we lost the file. So, sometimes you don't even get the paper. But the bottom line is, if you actually are on the Student Environmentalist Award list, that's like a pretty valuable thing to put on your like resumes and college applications and stuff. So even if you don't get the certificate, it's worth shooting for 15 hours by April 30th. Talk to Grace Silver because there's this thing called Earth Day coming up. Yeah.
I thought we don't get community service for these things.
What?
I thought we don't get community service.
I'm sorry about that misunderstanding. You do.
So we have to like skip it sign? No, she does it.
Speak to the speak.
Write your ID down and then she does it. Oh, okay.
It's all like built in. Welcome aboard. We got our crap together. Don't worry. You can stay ignorant. Yes.
How do you know like how many hours you've done? Like, does she have it recorded?
Grace Silver, Grace Silver, Grace Silver. Anything else? She does have a list. There's a secretary position at the Green Club. You should all be involved. Anybody else? Yeah. There might be one or two, but then there's this thing called Earth Day. So as long as you've got like a few hours, you can probably rack up the last remaining ones by the end of April. Anybody else? In the year 1970, blah, 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 some guy that was neither an author nor a scientist wrote a book called Ecotopia.
Nice.
Which is a book of environmental science fiction. And it's pretty bad. As far as literary value, it's pretty much one of the most infantile, worst books that has ever been written. You could write a better book. Every one of you. Even Hugo.
Go pretty low there.
It's not, yeah, really bad, yeah. It's a really bad book. But the premise is kind of relevant to our class. Get ready for your dreams to come true. The book is about Northern California, Oregon, and Washington seceding from the United States and becoming an independent, ecological utopian nation called Ecotopia.
Nice.
I only got a few minutes, so I really got to get through this. I don't mean to suggest that it's a good book. I want to be really clear that it's quite the opposite. It's a bad book. Okay. I said it's not good, right? We all agree. Moving on. It was shockingly prescient. Like, for somebody in the 1970s with like very little traditional science background and not necessarily a lot of information about like the future of our economy and stuff, the guy makes some predictions about the future that are like shockingly accurate today, and the ones that he was not necessarily right about, they're like what people are now talking about for the future. So his design for urban development is like spot on what we now call cutting edge urban development. And his like design for housing is like the trendiest type of housing today with a few weird modifications. And his vision for the people of the future is entirely impossible. That's why it's a bad book. But he has a lot of interesting ideas, and sitting around to think about the environmental future, I think it's kind of relevant to our class. It's also a really easy read.
Like we'd never call our seated stage Ecotopia.
No. But it's a very easy read. I read it in like 12 hours sitting on the beach one day. It's like super casual. You could read it in no time. And if you read this, I gotta finish. I'll keep you. I have other announcements. If you finish this by the end of spring break, there's a quiz when you get back. I'll tell you right now. The quiz asks you, how does Ecotopia solve the following environmental issues? So when you're reading the book, be like, oh, that's a solution to transportation. And like, oh, that's a solution to like forestry. And like, oh, that's a solution to like tax policy. And like, oh, that's a... And they're all environmental issues. My quiz is on the environmental solutions in this book. Super easy. You can check it out today. I have 117 copies for 171 students, so you have a 68.4% chance of getting a free book from me. If you want to share it with a homie, then that doubles your chances. Yeah?
What's the date of the
What?
The exact date.
April 6th. Okay. Yes. 5. No.
Would this come for this week?
It's detached from units. Anybody else? Now please be quiet. 23 of you can have a book. Some of you may not want one because you have to read it over the break. So how many people do not want a book? Say if you don't want a book now, you're going to lose your chance. Did you just decide to raise your hand, Raina?
Yeah.
Okay. And now, those of you who didn't want a book, please don't take one later. We're all going to stay late if you blow it. If you said no book, that's cool. You don't have to read one. It's just extra credit. It doesn't matter. Who would be willing to share? It's like, oh, I live right next door to so-and-so, and I'll read it pretty fast. Is there anybody here who could share with someone else? Fine, you selfish bastards.
I decided I didn't want one.
You decided you don't want one?
I don't want either.
Who else? Fine. Now, please come up and get your slip. If it has a B, go grab a book. If it's entirely blank, don't grab a book. Bring back my little yellow paper. I need the yellow slips back. I need the yellow slips back. Go grab a book if it has a B on it, and bring me the slip and the book.
Wait, so what happens when you get a blank piece of paper?
Like,
Who else did not get one? Don't put him in yet.
Don't put him back in. Jose, tell me.
Hold on to this, please. Hold on to this. Hold on to this. Now line up with your books. Now line up with your books. You give me your last name. Daisy, I need my grade book, child.
Oh, wait, Jose, I have a question.
You tell me the last name and I'll write you down. Thank you.
So I'm not going to be counted 6 with the or is that just not me?
I'll have to decide later. What's your book number?
11? Oh, 13. Wait, what book?
I got 98. Last name is Australia. Last name and number. Hello. Last name and number. Last name and number.
And that was for the photography. I know.
it's like, why would I sign up? To waste my time. It's like, really? You guys.
Everybody's next to Everybody got He's okay. He's my favorite.
You actually
Reporters.
that's our when you get somebody else to your to get one for you.
I know. I'm gonna buy your coffee to buy like what the other body. Piece of toast.
I'll just study other stuff. I got 6 study ideas. So he wants to look at it.
I don't know if actually your car.
Oh yeah, no.